Our last unit, the unit for which we just wrote the unit test yesterday, was on kinematics. Kinematics, we learned on the very first day of Physics 20, is the study of motion without regard to what causes that motion. We looked at speed, velocity, time, acceleration, displacement. We learned about vector analysis, two-dimensional, one-dimensional vector analysis with displacement and with navigation problems, those relative motion problems. But all of those things that we did, all of those questions that we did, all of those topics that we did involved just the motion, not what was causing the motion. In this unit, we're going to look more at what causes the motion. Now, that doesn't mean that we're going to completely forget about what we learned in our last unit. That stuff's still very relevant, especially the group B equations. They're still pretty relevant because, in the end, what causes motion will affect the motion itself. So we're going to still pay attention to motion, but we're now also going to pay attention to what causes the motion. One word answer for this. What causes motion? Yep, force. Good. So this unit, the unit of dynamics, is the study of forces. Now, I know when you guys were in grade 6, you did a flight unit. You learned about Bernoulli effect and lift and drag and all that kind of stuff, right? Talk about all those forces. You must have defined a force. You guys remember from grade 6 science what a force is defined as? It's a real short, real simple answer. We're not going to make it more complicated in Physics 20 than we did in grade 6. A force is a blank or a blank? A push or a pull. That's right. A force is simply defined as a push or a pull. Now, that push or pull can come from a person, or that push or pull can come from some inanimate object like a wind or something like that. The push or pull can come from some kind of electrical interaction or gravitational interaction or whatever. There's all kinds of places that push or pull can come from. But in the end, if something is pushed or pulled, then it must have had a force acting on it. Now, something that we didn't do in grade 6 science, the effects of a force. Okay, a force is a push or pull, and we know that there's all kinds of different kinds of forces like lift force and drag force and all kinds of other forces. But what are two things that a force can actually accomplish? Not the types of forces, but what do they do? What's one of them? Movement. Okay, so in other words, you can cause something to speed up. If something's at rest or moving for that matter, a force can cause that object to speed up. Okay, what else? What else can a force do besides causing an object to speed up? Yep. It could cause it to slow down. So if it's moving, you could cause it to move slower, or you could cause it to stop, which is slowing down, right? Speed an object up, slow an object down. Change shape. Interesting. Change shape. That's different than speeding up and slowing down completely, right? I'm going to come back to that in just a second, okay? It's a good answer, but let's come back to it in a second here. It can cause it to change direction. All three of those things, speed an object up, slow an object down, change an object's direction, all fall into the same category. Okay, the first thing that a force can do is cause an object to accelerate. Speed up, slow down is acceleration, right? What about changing direction? I'm driving in my car on the highway at 100 kilometers per hour and I go around a turn. I stay going at 100 kilometers per hour. How do we say that's an acceleration? How can we categorize that into the same thing as speeding up and slowing down? How do you define acceleration, Matt? Yeah, acceleration is the rate of change of velocity, not speed. So you don't need to change the speed to have an acceleration. You need to change the velocity. And velocity is a vector. So it has both magnitude and direction, right? So if we change the magnitude of the velocity, in other words, we change the speed, that's an acceleration, speed up, slow down. But if we change the direction of the velocity, whether we change the speed or not, it's still an acceleration. An object that's going around in a circle accelerates, even if it's going at the same speed. We call it a centripetal acceleration. We can accelerate an object with a force. Now, what's the other thing that we can do with a force? We can deform an object or change the shape of an object. We can squish the object. We can stretch the object. We can lengthen it. We can shorten it. If I sit on my chair right now, you don't notice this with your chair because you guys have those hard seats. I've got this nice cushy plush seat that I can sit on right now. You notice when I sit on this, I apply a force on it, right? What happens to the seat? Or at least what happens to the cushioning on the seat? It compresses, it deforms, right? I haven't caused the seat to accelerate. I haven't caused it to speed up or slow down. I've caused it to change shape. When I lean against the wall like this, I'm not causing the wall to accelerate. I'm actually changing the shape of the wall microscopically. It is a microscopic change in shape, but it is a real change in shape. When the wall pushes back on my hand, it changes the shape of my hand a little bit as well. When an object has a force applied on it, it must either accelerate or deform. Could it do both? Sure it could. Sure it could. Depending upon the object, it could deform the object and accelerate the object, change the direction of it or change the speed of it one way or the other. All right? I want to define a couple terms here, 3 terms actually on this page. Inertia. You guys remember from what, grade 6 probably, or watched Bill Nye videos and Bill Nye the Science. Inertia is a property of matter. Remember that? We all know inertia is a property of matter. Everybody in grade 11 knows inertia is a property of matter because you've all seen Bill Nye the Science Guy. But we don't know what inertia is other than a property of matter. What is inertia? Inertia is the tendency of an object to keep doing what it's doing. The tendency of an object to resist a change of motion. Let me write that down and then I'll explain it. The tendency of an object to resist a change in motion. You're driving down your car down the highway at 100 kilometers per hour. That car has a lot of inertia. It doesn't want to change its motion. It doesn't want to speed up or slow down. It has a tendency to keep going in a straight line at a constant velocity, a constant speed. Now, you can change the motion of the car. You can change its direction. You can change the speed of the car. But it has a tendency to not change speed and not change direction. It has a tendency to keep doing what it's doing. A better example of that might be something like a curling rock. A curling rock slides down the ice. It seems to keep going forever, right? And it, except for the spin, if there's no spin on the curling rock, it seems to go in a straight line. It has a tendency to keep doing what it's doing, to resist a change in motion. It wants to keep going in a straight line, and it wants to keep going at a constant speed. What about that train that's sitting on the tracks on the siding, just getting ready to go? It's not going yet. You ever try to push one of those things? Probably not. I haven't. But I can imagine if I did that it would be difficult to push, right? Why? Because that train has a lot of inertia. It's difficult to change the motion of that train. If it has a lot of inertia, it has a tendency to resist a change in motion. If it's moving, it wants to stay moving at a constant speed in a straight line. If it's at rest, it wants to stay at rest. It doesn't want to change what it's doing. So tell me what factor affects inertia. What is it that affects how much inertia the car has as it's going down the highway or the train has as it's sitting on the siding? Yeah. No, not the force. The mass, yeah. Right now, you don't really know the difference between mass and weight, so I'll give that one to you. Okay, it's not really actually weight. It's mass. There is a difference. You'll learn later on in the unit what the difference is. The mass of the object. The more mass it has, the more inertia it has. You know, a common misconception with inertia is that it has also to do with velocity. So the faster something's moving, the more inertia it has. That's not right. When you combine the effect of mass and velocity, we get a term called momentum. That's a physics 30 thing. We're not going to deal with that this year. Inertia depends only upon mass. A train sitting on the siding has just as much inertia just as much tendency to resist a change in motion as the train that's barreling down the tracks at 60 kilometers per hour. The speed doesn't matter. It's difficult to change the motion of the stationary train. It's difficult to change the motion of the moving train, equally so. So inertia, the tendency to resist a change in motion, is related simply to mass. The heavier something is, the harder it is to change its motion. The lighter something is, the easier it is to change its motion. Yep. Okay. Another term, static equilibrium. Before we do that, actually, let's define the two words that make up that term. What does equilibrium mean? Take chemistry, you might know what this means. Even biology, you might know what this means. Not so much neutral, no. Equilibrium means, right? A balance, yeah, it means a balance. So what does the word static mean? Yeah, not changing, not moving. So we're talking about a not moving balance here. We're talking, when we talk about static equilibrium, we're talking about an object at rest an object that's not moving with no unbalanced forces acting on it. Now that doesn't mean there's no forces. It means there's no unbalanced forces acting on it. John, can you give that desk in front of you just a little bit of a push here? Okay. Okay. Desk isn't moving right now, right? More or less, at least the desk isn't moving. John's pushing on it though. So we're not saying that when it's in static equilibrium, when it's at rest, there's no forces acting on it. We're saying there's no unbalanced forces acting on it. When John pushed forward, I pushed backwards. Those forces balanced. It's in static equilibrium, even though there's forces acting on it. It's in static equilibrium because there's no unbalanced forces acting on it. Another term, by the way, for unbalanced force is a net force. The net force is the total or unbalanced force acting on something. My net salary on payday is my gross salary. If you guys have a job, you'll see your pay stub. It's itemized like this. You see your gross salary. That's the amount of money that you make in the month or in the 2-week period or whatever your pay period is. Then they take off money for employment insurance and for Canada pension, and they take off money for income tax, and they take off money for this, or they take off money for that. Okay, my net pay at the end of the month is all those pays added together, everything added together, except my deductions would be adding together a negative number, right? So my net is my total or my unbalanced force. If you have an object at rest with no unbalanced forces acting on it or no net force acting on it, it will remain at rest. Translational equilibrium means balance, moving, something that's moving with things balanced. We'll say it's a moving object with no unbalanced force, or with no, we'll call it a net force now, with no net force acting on it. Doesn't mean there's no forces. When I'm driving my car down the highway at 100 kilometers per hour, the net force is 0. But there's a wind acting on it. There's a air resistance acting on it. There's an applied force acting on it. I'm going at a constant speed because the forces all balance. We're going to say a moving object with no net force acting on it remains moving a straight line at a constant speed. In other words, keeps doing what it's doing. If you're in equilibrium, the forces are balanced. If you're in static equilibrium, the object will continue to remain at rest. If you're in translational equilibrium, the object will continue to move in a straight line at a constant speed forever until acted upon by an unbalanced force, until there is a net force that acts on it. And no longer am I pushing one way, John pushing the other way, but rather John's the only one pushing, or I'm the only one pushing. Now, I want to kind of summarize a few of the things that we've said here in one straightforward statement or one law. We call it Newton's first law, also known as the law of inertia. It can be phrased in one of two ways. Well, in two ways. We have to include both. The first way, the first part of it says an object at rest will remain at rest. Why? Because it has inertia, and it wants to resist a change in motion. If it's at rest, it wants to stay doing what it's doing, which is nothing. It's going to remain at rest until, there might be a point when it starts moving at some point, until acted upon by an unbalanced force. The second aspect to Newton's first law, also known as the law of inertia, is that an object in motion will continue in motion. In a straight line at a constant speed. In other words, it isn't going to speed up. It isn't going to slow down. It's not going to stop. It's going to keep going in a straight line at a constant speed until acted upon by an unbalanced force. This is a situation, Ollie, that you were asking about, right? You're driving your car down the highway. You're moving in a straight line already because the forces are balanced. Somebody hits you. It's a head-on collision. Okay, your body wants to keep going forward in a straight line at a constant speed. Your car stops because there's an unbalanced force acting on your car. If you're not wearing your seatbelt, then there's no unbalanced force acting on you. You will keep going. It feels like you're being thrown forward, but you're not. Really, you're just going in a straight line. It's just your inertia. It's carrying you in a straight line at a constant speed until the windshield stops you or until the road in front of you stops you. I'd like you to work on a few questions, a few check and reflect questions for the next few minutes at your desks. I'll give you a little bit of time to work on page 142, number 1 to 4 and 6.